Let's do an experiment. Take a plank, divide it by 2 so that you know where the middle is, and make subdivisions equally spaced like a ruler, so that you know the position of any object that you were going to place there. Pin the center so that this ruler is allowed to rotate. Now if you place two identical masses at equal distance from the center, the system remains in equilibrium. The picture is symmetrical. Whatever happens on this side is the same as whatever happens on that side. The forces are equal. But the moment you change the distance for one of them, one side wins. And we say that the system now has an angular acceleration. Even though the forces are the same, the system will rotate this way. There is something similar to a force acting here. A force accelerates objects in a straight line, which is a linear dimension, and this thing accelerates things in an angular dimension. Although they are very similar, we need to make a distinction. So let's give it a name. Let's call it torque. So the first thing that we notice is that this thing that we call torque is proportional to the distance between the point where the force is acting and the point of rotation. The next thing we should notice is that if you change one of the forces acting on the plank, one side wins, producing an angular acceleration. So we can also say that the torque is proportional to the force. Now we can take these two ideas and put them into one single equation, like this. Some of you already noticed that the angle of the force also matters. A force acting on this side will not produce any rotation. Any other angle does produce a rotation. So we notice that when a force passes through the point of rotation, the object does not rotate. Look at this configuration. A cylinder free to rotate with a force acting on this direction does not produce any rotation. That's clear, because the force passes through the point of rotation, or I should say the line of action passes through the point of rotation. But imagine this configuration where the force does not pass through the center. In this case, the cylinder rotates. And we see it all the time. Like when I enter a room, I push a door this way to open it. I push it this way to close it, but no one pushes it like this. We all know the door does not rotate on this way, no matter how much force you want to put in it, because this force goes through the axis of rotation. So let me write here what we know so far. In all cases, the forces can be decomposed. When you break down a force, look for those components that do not produce any rotation and get them out of there. Notice that breaking the force into components will produce the same results as rewriting the distance between the point of rotation and the line of action of the force. The magnitude of the torque is always the force times the distance, provided that they are perpendicular to each other. Another way of saying this is that the magnitude of the torque is r times f times sine of the angle between these two vectors, which looks a lot like the magnitude of a cross product. Actually, it turns out that that's what it is. So imagine you have an object, let's say floating in space, and now you apply a force on it. If the line of action of the force passes through the center of mass, the object will accelerate in that direction. If the line of action does not contain the point of rotation, the object rotates, besides having a translational motion, of course. If somehow I fix one point of the object so that the object does not move, but it can still rotate, then this is what happens. It will rotate about this point. What we always want with these rotations is the shortest distance from the point of rotation to the line of action of the force. And the shortest distance is a line that makes 90 degrees. This is why the distance and the force need to be at 90 degrees from each other. Or we can break down the force into components and find a component that makes 90 degrees with this distance. So let's do this in baby steps. I'm going to ignore units for a moment. Consider this bar, free to rotate about this point. The length of the bar is 6 units, and this here is 1 unit. There is a force acting this way right here, with 20 units of force. Cool. What's the torque about this point? Well, step number 1, identify your point of rotation, this right here. Step number 2, identify the line of action of the force, this right here. Step number 3, find the distance between this point and that line. Cool, it makes 90 degrees, okay. Now you just multiply, you get 100. Was that difficult? No. What about this problem? Look at the details of the problem. Try to do it. You got it? That's right. This is the same as the other problem. The shape does not matter, because this distance is the same. If I put the force at an angle, then we have a more interesting problem. There are different ways of solving the problem, but they are all the same if you think about it. Let me show you. Let's break the force into components. You take one of these components and look for the perpendicular distance from the point of rotation to the line of action. Multiply these two numbers and you get the torque. Well, one torque. Notice the direction of rotation. Now take the other force and look for the perpendicular distance from the point of rotation to that line of action. Again, multiply these two numbers and you get the other torque. Notice that direction of this rotation. It is the same direction as the other one, so now you add them. If they were rotating in opposite directions, you indicate the directions with a plus or minus. Just like you do with forces. You know, whatever pushes in one direction, you call it positive, and whatever pulls in the opposite direction, you call it negative. Same here. Whatever rotates in one direction, you call it positive. Whatever rotates in the other direction, you call it negative. Anyways, add these two torques and you get 108. Cool. Some people prefer to use a different approach. You may want to find the distance between this point and that point and find the angle, so that you can put it there on that equation. There is more work involved here, but the result is the same. We can take a look at this triangle, and with this distance and this one, we can calculate the angle and this here, which is the hypotenuse. This is what we get. And notice that this angle is the same as this one. And theta is this number plus 37. Now you can take all these values and put them in the equation. You see? You get the same answer. You can also use r cross f, but for this you have to write the vector in a proper form. It does not matter what form you choose, as long as you're consistent. I will use this one. Now I want to do the same thing for the distance. I need to express it as a vector. Let's visualize this in a three-dimensional space. The piece of paper I'm using to solve the problem has two dimensions, this one and this one. I call them x and y. But the paper lives in a three-dimensional world, just like I do. So let me include that here. R and F are expressed in terms of these dimensions. Notice that R and F don't have any components coming out of the page. You can see that in here with these zeros. You can see it better from this angle. Now you create a cross product and compute. You see, you get the same answer. Notice the direction of this vector. It points along this axis. The direction of the vector indicates the direction of rotation. It follows one of the versions of the right-hand rule.